Hello everyone, welcome to my YouTube channel. You can follow me this channel, that is Mwalimu Omar Saadi. In my channel, you can get chemistry classes both at O level and A level. So in today's video, we will look at Dalton's law of partial pressure. So the Dalton's law of partial pressure states that the total mixture of gases is equal to the sum of the partial pressure of the constituent gases. For instance, if let's say we have P1, P2, and B3, if P1, P2, and P3 are the partial pressure of individual gases, so our total partial pressure will be P is equal to P1 plus P2 plus P3. So if the partial pressure of individual gases is P1, P2, and P3, the total partial pressure will be P1 plus B2 plus B3. So considering the ideal gas equation, we will have P1V is equal to nRT, and then B2V will be equal to nRT, and lastly B3V will be equal to nRT. So this simply means the partial pressure of P1 will be equal to nRT, and B2 will be equal to nRT, and the same applies to B3. Keep it in mind that volume and temperature are kept constant. So if we now combine the three equations, we will have P1 plus B2 plus B3, then bracket V, because V is common to all the three B, so we'll have is equal to N1 plus N2 plus N3, which is the whole of that bracket RT. So N1 plus N2 plus N3 simply means the total number of moles of the constituent gases. So we can call them NT, which means total number of moles of the three constituent gases. So we can have now BV will be equal to NT, which is the substitute of N1, N2, and N3, NT, then RT. So for instance, if we want to find, for example, the partial pressure of P1, we will have the partial pressure of P1 will be equals to N1 all over NT times the total number of partial pressure. If we want to find the partial pressure of P2, we will have N2 all over NT times the total number of partial pressure. And if we want to find the partial pressure of B3, we will have P3 is equal to N3 all over NT times the total number of partial pressure. So N1 over NT, N2 over NT, and N3 over NT is the mole fraction, mole fraction. So assume N1 over NT, assume we have X1, and N2 over T, we have x2, and N3 over Nt, we have got x3. So the partial pressure of P1 will be, x1 times the partial pressure of total partial pressure of the three gases, and P2 will have x2 times the total number of partial pressure, and B3 will have x3 times the total number of partial pressure. So x1, x2, and x3 simply means the mole ratio, the mole fraction, I mean. So from there, x1, x2, and xt, when they are added, they must give 1. So the sum of x1 plus x2 plus x3 will be equal to 1, which simply means the mole fraction of x1 plus the mole fraction of x2 plus the mole fraction of x3 must be equal to 1. So that is the state of Dalton's law of partial pressure. So we can have one example so that we understand the concept better. Let's do one example concerning Dalton's law of partial pressure. We can have this question. At a temperature of 300 K, that liters of gas X kept under pressure of 1 atmosphere and 15 liters of gas Y kept under a pressure of 2 atmospheres is 2 atmospheres is transferred to an empty 10-liter container. So question A is asking, calculate the total partial pressure inside the container. Calculate the total partial pressure inside the container. So let us reread the question so that we understand better. We're told at a temperature of 300 K, 30 liters of gas X kept under pressure of 1 atmosphere and 15 liters of gas Y kept under pressure of 2 atmosphere is transferred to an empty 10-liter container. Then we're told calculate the total partial pressure inside the container. Simply means the total partial pressure of the two gases. So we can have, first we can have our ideal gas equation, that is BV is equal to nRT. So first we need to get the number of moles of each gas. So number of moles of gas X will be equals to, since we have BV is equals to nRT, we can divide RT on this side, RT on this side, so that we will have number of moles of gas X will be equals to N is equal to BV RT. So P we have 1 atmosphere, volume of gas X we have 30 liter, R is the constant, which is 0.0821, and temperature we are given 300 K. So N will be equals to P, which is 1 atmosphere, times volume, we are given there 30 liter, all over. Then our R is the constant, 0.0821, times temperature of 300 K. So we'll have, let us use the calculator. So we have 1 times 30 is just 30, all over 0.0821 times 300, all over 24.63, which is equals to 30 divided by 24.63, so 1.218, which is roughly 1.22 moles. So that is the number of moles of X1, number of moles of, gas X. So gas Y, number of moles of gas Y will have N is equal to BV over RT. So our B of gas Y is 2 atmosphere, so N will be 2 times V, which is 50 liter, all over our volume, our R is 0.0821, then times temperature, which is 300. So we'll have 2 times 15, that is 30, all over. The same answer, because we have 0.821 times 300, that is 24.63. So we still have 1.22 moles, which means the number of moles of gas Y and the number of moles of gas X is equal. So the question was asking the total partial pressure, So we will have total partial pressure will be, total partial pressure is equal to the number of moles of the two gases. Since we have the moles of gas X and mole of gas Y, so we add those together. So that is partial pressure of total partial pressure is equal to N R N. So to get N, to get partial pressure, we divide VCO. So nRT all over V. So we'll have partial pressure of T is equal to, since we have our number of moles, we add 1.22 plus 1.22, that is 2.44 multiplied by R, which is a constant, 0.0821 times temperature, which we are given 300 K. So all over, the volume of the two gases is 10 because it was transferred to an empty container that is 10 liter. So we divide this by 10. So we'll have, let us use our calculator. We'll have 2.44 times 0.0821 times 300. So that is 60.097 all over 10, which is equal by 10. So that simply means 6.001, we round off 0.1. So this is the total partial pressure of gas X and gas Y. So any question you can ask through the comment. Any observations and comment and critics are highly welcome.